Guys, so welcome back. Today we're going to be going over the easiest little arc length formula you've ever seen, the polar arc length formula. So let's take a look at where it comes from. The polar arc length formula comes from starting with your parameterization for x in terms of r cosine theta and y in terms of r sine theta. X is f of theta cosine theta. Y is f of theta sine theta. Now from our parametric arc length formula, this is how we would compute arc length if you had your x and y parameterized. So it's dx d theta squared plus dy d theta squared. And we're covering the arc length from angle alpha to angle beta. When you actually do the product rule to compute dx d theta and dy d theta and simplify it, it ends up coming out to f of theta squared plus f prime theta squared. And we're integrating with respect to theta. So note, what is that f of theta? The f of theta is the r part. Let's highlight that. So this is assuming that the f of theta is the r. Okay, the one thing you want to make sure before you jump in is you want to make sure that your curve isn't retraced on alpha beta. So when you're talking arc length and your function, if it repeats, you'd want to calculate the arc length and then just multiply it if you keep looping around. So for instance, on the circle, we know that a circle is given by r equals some constant and it's 2 pi periodic. So then once you go around 2 pi, you've already calculated the arc length of that circle. So you wouldn't want to compute that formula from 0 to 2 pi or 0 to 4 pi. Okay, let's take a look at some examples. So first we're going to find the arc length for r equals e to the theta on 0 to 2 pi for our theta values. So let's compute our f of theta and our f prime of theta. F of theta is given, f prime of theta is just e to the theta. And plugging into our formula, we're going to need to compute f prime of theta squared, which would be e to the theta squared, e to the 2 theta when simplified. So let's go to our formula. 0 to 2 pi, and then plugging into our formula we get square root of f of theta squared plus f prime of theta squared which we already calculated was e to the 2 theta. D theta. So simplifying this, we get 2 e to the 2 theta inside a radical. And when we integrate this, we can pull out that root 2 using our properties of radicals. Okay, before we jump into integrating, notice that we can actually compute the square root of e to the 2 theta, and it is e to the theta. So then we compute the antiderivative, we get e to the theta, evaluated from 2 pi to 0, and that root 2 out front. So we get root 2 times e to the 2 pi minus e to the 0, and anything to the 0 power is 1. So our answer is just root 2, e to the 2 pi minus 1. Okay. Let's move on to the next example. So our r is sine cubed theta over 3, and we're trying to find the arc length from 0 to pi halves. So starting off, we're going to find our f prime of theta. Using our chain rule, that's 3 sine squared theta over 3. Chain on the derivative of sine of theta over 3, which is cosine theta over 3. Chaining on the derivative of what's inside, which is 1/3. And when we simplify that, we get sine squared theta over 3 cosine theta over 3. So when we square that, which is going to be what plugs into our formula, we'll get sine to the 4th theta over 3 cosine squared theta over 3. Okay, so now we're going to go and pop that into our formula. We're going from 0 to pi halves, and we have the square root of f of theta squared. So sine cubed squared would be sine 6th theta over 3 plus sine to the 4th theta over 3 cosine squared theta over 3. Okay, now when we go to integrate this, this is a fat mess, right? So I really don't want to leave it looking like that. Instead, I'm feeling some trig identities to hopefully put everything in terms of sine and maybe get some common terms that we can combine. So I note that cosine squared is equal to 1 minus sine squared, keeping the argument the same. And then this becomes sine to the fourth theta over 3 times 1 minus sine squared theta over 3. And we still have that sine to the sixth theta over 3 in there. Okay, so let's clean up what's inside the radical. Looks like when we distribute, we're going to get sine to the fourth theta over 3 positive, and we're going to get minus sine to the sixth theta over 3 when we distribute that term out. So when we clean this up, we're going to get all inside the radical. Looks like we're going to have a sine to the sixth plus sine to the fourth minus a sine to the sixth. And check it out. Sine to the sixth, sine to the sixth cancels. So when I compute this square root, I'm taking the square root of sine squared, and I'm going to be left with sine squared. Okay, so let's use our trig identities to help us here. When we integrate sine squared, remember we want to use our double angle formula, or rather half angle formula, sorry. Okay, so remember that it's 1 minus cosine, and you do 2 times the angle that you see on the squared version. So that would be 2 theta over 3, and this is all over 2. And we're going 0 to pi halves. So when we go ahead and integrate that, we get 1/2 times theta minus 3 over 2 sine of 2 theta over 3, and that is evaluated from pi halves to 0. So when I plug all these numbers in and I simplify using my special triangles to help me out with that, I get 1/2 times pi halves minus 3 root 3 over 4. And cleaning that up a little bit, as clean as it'll go, we can distribute the half through and combine fractions. This part is definitely not necessary, but a textbook would probably want to put it in terms of one fraction, so I'll go ahead and do that. It would be 2 pi minus 3 root 3 over 8. So either one of these would be okay with me if I saw them. Pretty straightforward. So the arc length formula, just once again, so we see it as the last thing. You integrate from alpha to beta. You make sure that your curve isn't being retraced on alpha beta. And you take the square root of f of theta squared plus f prime theta squared with respect to theta. Hopefully this helped you guys. See you next time.